Let me welcome you to this lecture. We have been discussing the chemistry of hydrides of boron, it is about boranes, and so far we have looked at the kind of bonding, or we have learned about the uh, unique bonding present in these boron hydrides, as well as we have also looked at a very interesting method called the Sykes number, which allows us to predict the number of different types of bonds present in a give borane molecule by just looking at the stoichiometry or formula of the borane molecule. So let us proceed further and then now discuss about different classes of or different series of boranes that we can categorize by looking at the formula as well as the structure of the borane molecule. So according to the structure as well as the stoichiometry, the boranes can be classified into 5 different categories, and these are we will discuss about these categories or these classes of borane molecules now. So the first class of borane molecule is known as closoborane, and the general formula for the closoboranes is BnHn2 negative. So N can be anything between 6 and 12, and for these boranes, these closoboranes with N equal to 6 to 12 are well known. Now, why we call these boranes as closoborane? Because this word closo comes essentially from a Greek word called klos, which means cage. So for the closoboranes, so the structure of these closoboranes is like cage, like the structure is cage-like, and the structure of these closoboranes are essentially uh, they have structures which are polyhedral cage-like structure. So we already know, or we should know about what do we mean by polyhedron. The word polyhedron essentially means structures like octahedron, tetrahedron, dodecahedron, icosahedron, these sort of structures where there are triangular faces in these structures. So this word hedron essentially stands for triangular faces, and these structures essentially have different number of triangular faces, and that is why we call them as, or we categorize them as polyhedrons. So these closoboranes have polyhedral cage-like structures, and we will draw some of these structures during these lectures. So now, uh, in case of a closoborane, the N boron atoms in the closoboranes essentially occupy the boron atoms occupy n corners, or we can write all n corners of a n cornered polyhedron. So all the corners or all the apex of the polyhedron are occupied by the boron atoms in closoboranes, and that is why the structure is closed structure, and we call them as, and that is the reason why we call them as closoborane. Now, the next category or next series of borane is known as nidoborane, and the word nido essentially comes from again a Greek word called nidas, which means nest. This essentially stands for nest-like structure, and the formula of, or the generic formula of nidoboranes is BnHn plus 4. So in this case, the structure is open cage-like structure, like nest-like structures, and the structures essentially are such that where the boron atoms occupy n corner or there are n boron atoms. So the n boron atoms essentially occupy n corners of a n plus 1 corner polyhedron. So the structure is based on a n plus 1 cornered polyhedron, and in this n plus 1 corner polyhedron, one of the corner is not occupied by any boron atom, so it is open in that corner, is empty, and that is why the structure is open, and all the other boron atoms, essentially the n boron atoms in this nidoborane will occupy the n corners of the n plus 1 corner polyhedron. So next category or next series of borane molecule are known as borane, and arachno again comes from a Greek word called arachne, which essentially stands for spider's web. So these borane molecules have wave-like, spider wave-like structure. The structure is even more open than the nidoboranes, and the structure is again the boron atoms occupy n corners of a n plus 2 cornered polyhedron. And the generic formula for arachnoboranes is BnHn plus 6. That is the generic formula of arachnoboranes. And there is another class of borane, which is known as hypoborane, which is even more open structure than nido or arachnoboranes. And the hypoboranes, again, the word hypo comes from the Greek word hyphae, which means net. So these structures are essentially completely open structure or net-like structure, and the formula of or the generic formula of hypoboranes are BnHn plus 8, and here B atoms occupy, again boron atoms occupy n corners of a n plus 3 cornered polyhedron. So if you take a n plus 3 cornered polyhedron, then 3 of the corners are essentially left empty without any boron atom, without any atom there, and the structure will be more or less like a net-like structure or open structure, and these are called hypoboranes. So we have seen 4 different series of boranes, or we have categorized the boranes according to their stoichiometry or the formula, and as well as these boranes molecules essentially have a different structure as well. As we have seen, for the closoboranes have cage-like structure, while nidoboranes, the structure is more or less more open and nest-like structure, and arachnoborane is a spider web-like structure, which is even more open than the nidoboranes. And in this case, we have the structure is based on n plus 2 cornered polyhedron, where 2 of the corners are left empty, and that is why the structure looks like wave-like structure. And the last one that we have learned is the hypoborane, where which is based on n plus 3 cornered polyhedron, where 3 of the corners are left empty without any boron atoms, and the structure is net-like structure essentially. And there is another type of borane apart from these 4 categories of borane, which are known as conjuncto borane. These are hybrid structures essentially formed by combination of any 2 of these borane structures, or when we join together 2 borane molecules having 2 different structures like closo or nido or arachno, these sort of structures, then we call them as conjuncto borane, because they do not fall into any of these 4 pure structural types. So these are the different types of boranes, or we can classify the boranes according to the stoichiometry as well as according to their structure in these 5 different categories. So let us now try to draw the structure of some of the borane molecules. So first we will try to draw the structure of some of these chloroborane molecules, because these structures are cage-like structures based on different polyhedral structures, and that is why it should be easy for us to draw these structures. So the structure of, let us draw the structure of B6H6 2 negative. That is it. By looking at the formula itself, we can say that this is a structure again, because there are 6 boron atoms, so the structure should be based on a 6-cornered polyhedron. So we know that such a polyhedral structure which has 6 corners is the octahedron. That is, we can draw the structure of B6. So what we can do is that we can make these lines, we can darken these lines to give it a 3-dimensional impression, and in all of these corners of the octahedron, the boron atoms, these are all boron atoms lie on the corner of the octahedron, and to each of these boron atoms a hydrogen atoms is essentially attached. So that is what is B6H62 negative. We have drawn the structure of B6H62 negative. Now when we draw the structure of these sort of borane molecules, we should make it very clear that these lines essentially draw the polyhedral skeletal structure of the boranes. These are not bonds. This does not necessarily mean bonds between this boron atom and this boron atom here. These lines that we have drawn to 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 show the octahedral structure are not bonds. These are not real bonds. These are only drawn to show the structure of the borane molecule. But when we draw these BH, the lines over here, these BH, these are all real bonds here, because there is a linkage between this boron atom and this terminal hydrogen atom. There is a covalent bond between them, and these essentially make bonds, while these lines which define the polyhedral structure are not bonds. So this is the structure of B6H62 negative ion. Then we can also draw the structure of B7H7 2 negative. So this is octahedron. B6H62 negative is based on octahedral structure. Octahedron, there should be 8 triangular faces in the octahedron, and if you can count that if there are 8 triangular faces or not. On the top over here there are 4 triangular faces, and again on the bottom here there are another 4 triangular faces, which makes it total 8 triangular faces, and that is why we call it the octahedron as octahedron. So now this B7H7 2 negative will again be based on, we know it should be based on a polyhedron with 7 corners, and in all of these 7 corners a boron atom should be placed, so that the structure is essentially closed cage-like structure. So let us try to draw such a polyhedron. So we know such a polyhedron which has 7 corners is the pentagonal bipyramidal structure. So again, let us darken these bones to get a 3-dimensional impression over here, and the bones which are behind us, we make them as dotted lines, not bones exactly. uh, these are not bonds, we have already said. Uh, the outer periphery of these polyhedral structures, or the lines which define the outer periphery of the polyhedral structure, are essentially these are, and we draw these, the ones which are behind us, we use dotted lines to define those particular lines over here. And so this is the structure of B7H7 negative, 2 negative, and to each of these boron atoms, which will again place 1 hydrogen atom. So this is the structure of B7H7 2 negative, and what we see, it is based on a polyhedron with 7 corners, and on each of these corners of this 7-corner polyhedron there is a BH group is essentially there, and this closes the structure, or the structure is completely closed and cage-like structure again. So let's draw the structure of B8 H8 2 negative then. So that is the structure of B8 H8 2 negative. Again, let us place the hydrogen atoms. Let us put hydrogen atoms on each of these boron atoms in this 8-corner polyhedral structure. That is the structure of B8 H8 2 negative. Again, we see that the structure is completely closed or cage-like. Then let us draw B9 H9 2 negative. So that is the structure of B9 H9 2 negative. We should have made this line also dotted, just to make sure that we get the impression that this is behind us, while the bold lines over here, or solid lines here, are towards us. So that is how we can make the structure look better, or we can get the 3-dimensional impression on this polyhedral structure. Then let us proceed further and then draw the structure of B10 H10 2 negative. Slightly make it longer. So again, to each of these boron centers, you should attach a hydrogen atom. Total 10 boron centers. So that is the structure of B10H10 to negative. One should darken these bonds again to get the three-dimensional impression here. This sort of structure. So next we will draw the structure of B12H12 to negative, which is based on the icosahedral structure, or this essentially has got 20 triangular faces, icosahedral. Just darken these bonds. So we can count if there are 20 triangular faces or not in the icosahedral structure and then verify. Now to each of these 12 boron centers, a hydrogen atom is again attached. One has to place the hydrogen atom when we are drawing the structure of the B12H12 to negative. So B12H12 to negative. So we have drawn the structure of several of these closo-borane molecules. Now we will try to draw, or we will see how we can draw the structure of a nidoborane or say arachnoboranes. We have learned that in case of the nidoborane, the structure is essentially based on a n+1 polyhedron, and then if in these n+1 polyhedron or n+1 corner polyhedral structure, if one of the corner is left empty, then it will become a nest-like structure, and it will have it will be essentially the structure of a nidoborane. So if we start now, so to draw the structure of nidoborane, or say to draw the structure of arachnoborane, it is better to start with the structure of the parent closoborane. So if we want to draw the structure of say B5H9, so we will start with the structure of the parent closoborane, because we know this B5H9, that is the N here is equal to 6. So the structure of B5H9 should be based on octahedral structure, or it should be similar to the parent structure is essentially coming from B6H62 negative. Now if you take the octahedral structure and remove one of the corner or remove one of the boron center in one of the corners of this B6H62 negative, then we will and then add the required number of hydrogen atoms, then we will get the structure of B5H9 or the nidoborane. So let us do that. Let us remove one of the BH group here, and once we remove one of the BH group, then we will end up with H5 to negative here, and then let us add 4 4 protons, so to get the structure of B5H9, so plus 4 hydrogen here. If we add, then we will get the structure of B5H9. So what we have to do, we have to wipe off one of the corner uh, of the hadron. So let us do that. Let us once again draw the octahedron here and then wipe off one of the corner. So this is the octahedral structure we have drawn once again, and let us now wipe off one of the corner of this octahedral structure. Then we should get the structure of the nidoborane B5H9. So the structure of the nidoborane should be somewhat like this over here, but then because nidoborane B5H9, because we know in this case for the B5H9 structure should be based on n plus 1 polyhedron, which is octahedron essentially. 5 plus 1 gives us equal to 6, and one of the corner will be left empty. That is what we have done. We have removed one of the corner of the octahedron, and then we end up with this structure. Now we have to add the required number of hydrogen atoms here to each of these boron atom in the corners. You add a BH group, or you add a hydrogen atom, and then the rest of the hydrogen atoms will be added as bridging hydrogen atoms. So we have to add 4 more hydrogen atoms as bridging hydrogens over here. So let's add these hydrogen atoms as bridging hydrogen atom between the boron centers over here in this way. So that is the structure of the nidoborane B5H9. So now we know how we can draw the structure of a nidoborane. We just need to start with the parent closoborane and then wipe off one of the corners and then add the required number of hydrogen atoms to get the structure of the nidoborane. So then let us also proceed further and then remove one more corner, and then we will end up with a arachnoborane, because we know for the arachnoborane the structure is based on a n plus 2 polyhedron. So and then two corner of these n plus 2 polyhedron are essentially left empty, so that the structure becomes wave-like structure. And here what we have seen, that the structure is becoming now nest-like structure, because it is no longer a cage-like structure and the structure is nest-like. So that is why it is called nidoborane. So now let us proceed further and then see if we can get the structure of B4H10, which is then arachnoborane. By looking at the formula itself, we can say it is BnHn plus 6 generic formula. So that is why it's a arachnoborane. And for this again, the structure of B4H10 should be based on an octahedron. The parent structure is octahedron once again, because the n here is equal to 4. So n plus 2 corner polyhedron the structure is based on, which is an octahedron. And if we remove 2 of the corners, or if we leave 2 of the corners of this octahedron empty, then we will end up with the structure of B4H10. So let us remove one more corner of the octahedron from here. We can start with the structure of B5H9 itself, and then draw the structure of B4H10 here. So what we have done here, we remove one more corner of the octahedron here, so we will be left with this sort of a basic skeleton here, and then we have hydrogen atoms, the bridge hydrogen atoms, and also the terminal hydrogen atoms on the boron centers here in this way. But then if we count the number of hydrogen atoms, what we see here is yes, this is 3, 4, 5, 6, 7, 8, total 8 hydrogens are there. We still need to add 2 more hydrogen atoms, and these 2 hydrogen atoms are going to be present as BH2 hydrogen atoms, and then the other 2 boron atoms, or there will be a BB linkage between the other 2 boron atoms. So this is the structure of B4H10, or we can draw the boron centers as well here we can draw the structure in this way. So that is the skeletal structure of B4H10. Now we will draw the real structure here, showing the linkages between the individual atoms. So that is the structure of V4H10, and we see its structure is like a spider wave-like structure, or the structure is more open as compared to what you see for closoborane or say for arachnoborane, and the structure is now a wave-like structure, a spider wave-like structure, and we can get the structure starting from the parent closoborane and then successively removing two boron centers into two of the corners of the polyhedron. So this is how we can draw the structure of closoboranes, nidoboranes, as well as arachnoboranes, and this essentially brings us to the end of this lecture. And what we have learned during this lecture is how we can categorize the boranes by, in terms of their stoichiometry or in terms of their structure. We have seen that there are 5 different series of boranes. The closoborane, nidoborane, arachnoborane, hypoborane, and conjunctoborane. We have looked at the general stoichiometry of these different types of boranes for all the types, all 5 series of boranes here, and also we have looked at the structure of these borane molecules. We have seen that closoboranes derive their name because the structure is cage-like, while in case of nidoborane the structure is nest-like, and that is why we call it nidoborane. And for arachnoborane the structure is spider wave-like, while for hypoborane the structure is net-like structure or completely open structure. And then we have drawn the some of the structure of some of the closoborane, and we have seen that these borane structures, closoborane structure, are essentially polyhedral structures or polyhedral cage-like structures. And then finally we have seen how we can draw the structure of the nidoborane as well as for the arachnoborane, that we have to start with the parent closoborane and then wipe off or remove the required number of boron atoms in one boron atom in one of the corner of the polyhedron for nidoborane, while for getting the structure of arachnoborane we have to remove 2 boron atoms in 2 corner of the polyhedron or parent polyhedral closoborane structure to get the final structure of the arachnoborane. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.